All right, why don't we ready with the video? Okay, why don't we go ahead and get started. So welcome back everybody to EE290C. Obviously the project is due in about an hour and 20 minutes or so, so I think people will be slowly trickling in as that happens. So just one side note, I haven't posted the official thing yet, but obviously Project Phase 4 is the next and final step. Hopefully pretty much what you should be doing there is obvious. It's really just building the rest of the adaptation loops and then actually really trying to finalize the circuit designs as much as you possibly can. So as I said, I'll post some stuff about that. There will be another sort of series of presentations that we'll do. So that'll be sort of like the final quote-unquote steps of the class. And actually that first set of presentations will be starting 2 weeks from now. Somewhat differently from the previous phases, the actual final report will be due after those presentations. So still have a chance to give you feedback and to go back and sort of change things based off of that. But we'll see sort of how things go there. The other thing I should mention is there was a request for me to do some, let's say, bonus lecture kind of thing on just what I would have done for the project, what I saw that I thought was interesting and stuff like that. If people are interested, I'm happy to do that. We won't do anything official or anything, but maybe I'll just have a lecture at BWRC or something like that. So if people are interested, certainly let me know, and we can figure that out kind of as we go. Just as another, let's say, logistical note, we're coming towards the end of sort of the core, let's say, class lectures. I think we've basically got only 4 more lectures left to go, so that's this week and next week. So we'll basically be sort of wrapping up all of the, let's say, core part of the material probably by the end of this week or so, and then next week I'll probably maybe spend lecture and a half, just kind of on more advanced topics or things that you might see out there, either in the future or in fact in the past that maybe were abandoned and may eventually come back into flavor. So before I kind of dive back into material, any kind of questions or issues or anything like that?
Can we get the extension on the project phase 3 report?
Phase 3. So that's partially difficult for me to answer now, but you should send in whatever you've got. And by the way, again, the point of Phase 3 is to make sure you guys are working on track so that people don't start like a day before the thing is due and expect to be able to finish. So in terms of, let's say, the grading or whatever, Phase 3 is not going to be the critical part of the grade. It's really Phase 4 that's the most important part of it. So I'll put it this way. You should turn in whatever you've got. How's that? Other questions or issues or anything like that? Okay, so if not, let's actually go ahead and kind of dive back into the class material. So last time we spent a bunch of time talking about phase interpolators and sort of all of the different issues and how you really implement them. And basically at the end of the class, we really sort of just mentioned that, we kind of went through, let's say, the traditional phase interpolators, but towards the end we sort of got into another potential approach for how you could build them, or at least we started talking about it, which is basically this injection locking idea. Okay? So the basic idea with injection locking is that there's this fairly interesting phenomenon where if you take an oscillator and you somehow couple some energy into it from another oscillator, and that other oscillator maybe is at nominally a slightly different frequency, if they're close enough and there's sort of enough coupling between them, what you'll see is that over time they will actually lock onto the same frequency. Okay? Now, the other interesting effect of that is that because their nominal frequencies are slightly off from each other, that basically has the effect of actually moving the phase relative to each other. Okay? Now, this is interesting in this context because remember the whole point of a phase interpolator was just to act essentially as some sort of programmable phase shift. Okay? And so as we described a little bit last time, as we were saying, the reason that phase shift happens is that when the frequencies are slightly off from each other, you can kind of interpret that as being the edges in those, let's say, 2 different frequencies are kind of being interpolated together, right? And so the more you move those frequencies apart, kind of the more you're interpolating between those 2 edges, okay? So, as I mentioned, this is actually sort of an interesting thing in the context of a phase interpolator because what you can imagine doing is basically intentionally tweaking either the injection frequency or the nominal frequency of the oscillator itself in order to create exactly that programmable phase shift kind of effect. Okay? So let me just sort of draw a picture of how something like this is typically done. Okay? So what you typically do is you take something that looks a lot like essentially an oscillator to begin with. And in particular, this is often done with LC oscillators. So you might just have something that looks sort of like this. Okay? And then what you'll typically do is you'll take whatever the clock is, which is, let's say, what you want it to be the nominal frequency of the link. And then what you'll do is you'll actually inject that clock into this oscillator. Okay, now there's many, many different ways you can do that, but this is just one particular example here. Okay? Okay, so now if you do this, and obviously if I really wanted to use this as a phase interpolator, then I kind of need some programmable phase shift. Okay, and by the way, you should sort of interpret this phi injection here. That's kind of like your reference clock that's maybe coming from the PLL that you use to sort of generate that clock in the first place. Okay? So if I want to turn this into a phase interpolator, turns out all you really have to do is tweak that capacitance there. Okay? Because basically by tweaking that capacitance there, what you're really doing is you're changing the nominal frequency of that oscillator, right? And then by changing that nominal frequency, what's going to happen is you're also going to be changing the phase shift relative to that injected clock. Okay? Kind of intuitively, by the way, one way you can sort of see that is that, if I'm changing that capacitance, which means I'm sort of changing, let's say, the nominal frequency, if you look at the phase of that tank versus frequency, and now I'm just looking at the sort of passive part of the network, right? If it's a reasonably high Q kind of thing, what you'll see is something that looks sort of like that, right? So you go from sort of right at the resonance frequency, you're at 0 degrees, and you go from plus 90 down to minus 90 degrees. Okay? Well, if you basically shift that tank so that you're no longer operating right at that resonance point there, right? Maybe let's say you're shifting it, I don't know, off to be like right here, right? Then what you're basically doing is you're introducing some phase shift. Okay? And if you're basically introducing a phase shift, that's again exactly the kind of effect that we're looking for in terms of doing this phase interpolation. Now, the only additional thing that's a little bit, let's say, funny about this is that we're still forcing it to operate at a given frequency set by that injection signal. It's just that by tweaking the tank, we're effectively creating that phase shift. Okay? So there's lots and lots of math that people do to sort of figure out exactly what that phase shift is and what the characteristics are. I can point you to some references if you're interested. But the bottom line is that you typically will end up with curves that look something like the following. So what you'll typically have is something that looks like if this is your sort of phase shift, and this is, let's say, the digital code that you use to control the capacitance, and let's say that increasing that code increases the capacitance, what you'll typically see is curves that look something along these lines. Okay, and I maybe exaggerated the nonlinearity a little bit, but something along those lines. Okay? So basically, again, if you sort of line everything up onto that nominal frequency, right, so that the tank is really lined up with the injection frequency, then you get sort of 0 degree phase shift. But then as you move either above or below that tank, you'll be creating some additional phase shift. Okay? So it turns out you can actually get a pretty wide range of phase shift out of this, but you have to do some, let's say, clever designs with how strong of an injection you do, and sort of really understanding the dynamics of this whole process. But this is a reasonably sort of interesting thing to do, especially in forwarded clock systems, right? So remember, in forwarded clock systems, you actually have a reference clock coming into you, right? So if you have a reference clock coming into you, then really the only thing you have to do is just figure out what the right phase actually is, right? So what you could do is you could take that reference clock, use it to inject into this thing, and then just use some other CDR-looking kind of loop to just adjust this nominal frequency to get yourself to the right actual phase position. Okay? Does this make sense to people, or? Yeah.
So if you have the forwarded clock, how would you compare this versus just a delay line?
Say that again?
How would you compare this with a delay line?
Okay. So it depends how you build the delay line, obviously. But imagine that I'm doing, let's say, a 20 gigabit per second link or something like that, right? And let's just say that I have, I don't know, as an example, a 10 gigahertz forwarded clock. I'm just making it up, right? So I could indeed take that 10 gig clock and then, shove it through some CMOS delay line or something like that, right? But by the way, if I do a CMOS delay line, then I need really, really precise sort of resolution on those phases if I'm just doing a picking. If I'm doing phase interpolation, then I need delay line plus I need that phase interpolation afterwards. Whereas here, notice, I just have basically this one stage, right? Basically, all I do is I just take that clock, I shove it into this thing. It acts both as sort of a buffer and as doing this phase shift, so to speak. So I think in many ways that's sort of a complexity argument. The other thing is that since this is sort of based on an LC tank to begin with, that does mean that you can tend to push it to higher frequencies than you otherwise could have, right? So if I was, let's say, doing a 20 gigahertz clock or a 30 gigahertz clock or something like that, shoving it through a CMOS delay line might have gotten pretty painful at some point.
Do you get any filtering from the Q of the tank? Or
Okay. So the question was, do you get any filtering from the Q of the tank? It's a good question. Now, so let's say that you were really lined up exactly on the right clock frequency, right? Then indeed, you'd try and make the Q of the tank sort of as high as you could possibly make it, right? And then you would indeed sort of get, let's say, a good filtering, or you'd basically be making that quote-unquote oscillator as clean as you could make it. But remember, you're trying to make sure that you can actually lock this thing onto an input clock. So the question really becomes, how big of a range and difference in frequencies is there between that input clock and the sort of nominal frequency you're going to get from that tank? That will tend to sort of cause you to reduce the Q somewhat. But there's also some pretty, let's say, detailed considerations about sort of so-called how strong of an injection you're doing, right? And you can kind of think about it, the stronger of an injection you're doing, the more the phase noise is just controlled by whatever it is you're injecting and not by the actual characteristics of the tank itself. So usually you'll often sort of flip it around the other way. Often you'll make it so that the phase noise really is set by the signal that you're injecting rather than by sort of the fundamental characteristics of the oscillator by itself. Other questions on this? Or? Okay, great. So again, just wanted to mention this one because it is an alternative that I've seen sort of popping up in a few more places. It also has some interesting characteristics in that it turns out you can actually injection lock things not just sort of at the fundamental frequency. So as an example, if you wanted, let's say, 10 gigahertz at its output, it turns out you can actually injection lock it to something that's even a lower frequency than that. Right? So you could inject, for example, let's say a gigahertz or even 100 megahertz if you're really aggressive and potentially still get them to lock. You can actually go the other way as well. You can have things that would come in and inject at 20 gig but lock, let's say, like a 5 or 10 gigahertz oscillator. Okay? So there's some pretty clever things that people have been doing using these kinds of techniques, and that's the main reason that I sort of wanted to mention it, just so people are sort of aware of the basic idea of how these things work. Okay, so unless there's any other questions on this, let's actually go ahead and move on to the next set of slides. Okay, so turns out in terms of, let's say, all of the kind of core components that you might see in a high-speed serial link, we're now actually basically done. Okay? So what I'm going to be doing in the next couple of lectures is talking about things that are quote-unquote, let's say, support types of functions. Now, it turns out that those support functions actually can be pretty critical and can sort of make or break whether things really work or not. But, this wouldn't necessarily be traditionally what you'd think of as being, let's say, the key thing when you first think about building a high-speed serial link. But as you'll see, these things actually, sort of pop up fairly often. And so the main thing that I'm going to talk about, at least for, let's say, probably the next week or so, is actually how you do supply regulation in an efficient and really, I should say, sort of high supply rejection way. Okay? And I guess maybe I should mention, as I said, this is not, something that would typically be considered as part of a high-speed links class. But hey, this is something I did my PhD on, and turns out it is pretty useful, so I figured I might as well talk about it. Okay, so now, just as, let's say, further motivation beyond that as to why you might want to do something, or why we're really talking about this, I just want to remind you all that, we've talked a lot about the links themselves, but remember, they're always placed into a bigger context, right? And in particular, a lot of these links actually show up on pretty sophisticated digital chips. So just as an example, if you look at any of sort of the modern microprocessors, they've now actually got something up to about 6.4 to maybe even 10 gigabit per second serial links integrated onto them. And not just one, but actually multiple. Okay? Well, that has some pretty interesting implications from the standpoint of you designing your link, right? Because most of you guys are trying to get signals on the order of maybe 20 to 50-ish millivolts, kind of the input of your slicers. Maybe 100 if you're really, really good. Well, don't forget, if I've got this, microprocessor all around me, and by the way, those processors, for today, especially if you're talking about a server processor or something like that, it's probably dissipating over 100 amps or so at around a 1 volt supply voltage. Okay? And by the way, that's not necessarily DC current. That's, if you do one computation this cycle, it's one current. If you do another computation, it's a different current, and it's kind of constantly bouncing around, right? So the reason I mention this is that if you sort of think about it, if you've got something that's a 1 volt, 100 amp kind of beast right next to you, that means the impedance of the power supply feeding that thing needs to be on the order of 1 milliohm. And that needs to be on the order of 1 milliohm kind of from DC to daylight, just to give you a sort of 10% supply ripple spec. Okay? So how many of you guys have ever actually, seen or handled a 100 amp cable before? Yeah, exactly, right? Nice fat monster, right? Now, okay, these processor chips, they're big, but they're nowhere near that big, right? They're like, okay, maybe if they're really, really pushing the reticle, they're maybe like 20 by 25 or something like that, okay? But still, nonetheless, you got to be shoving that 100 amps into that thing, okay? So again, the whole point of mentioning that is just that it turns out it's pretty darn tough to get that low of a supply impedance, especially across all of the different frequencies you might be interested in. Okay, so even if you get it at DC, there's a lot of inductance just, getting through all the package, through the PCB, getting into the chip, right? You'll maybe put some decoupling cap on the chip, but hey, at the end of the day, you want a chip that's more than just decoupling cap. It, should actually be doing something, right? So just to convince you as to why this is a problem, this is actually some, let's say, measured pictures of what you might see on one of these microprocessors. So this is something from the particular processor that I'm showing you right there. You can kind of interpret this as a lot like, let's say, kind of like an eye diagram, but like a statistical eye diagram. So it's kind of telling you probability of the supply voltage being at certain values at different points in the clock cycle. And kind of the take-home message here is that indeed you can see a pretty wide variation in the possible supply voltage values. Okay? So again, the point there just being that, if you're going to be building your link, and that thing's going to be integrated onto the same chip, well, a lot of the times, your link's power supply may actually be shared with the rest of the chip. Or even if you get a separate power supply, your ground may actually be shared with the rest of the chip. And even if you don't, you're on the same substrate. Okay? So even if you try and separate all the power rails, you'll still actually have pretty reasonable coupling between things. Okay? So that basically says that you really have to sort of worry about what is this supply noise actually going to do to the performance of your link. Okay? Now, in particular, because of sort of these really big supply noise things that will tend to kind of corrupt your very sensitive signals, that's really why it's actually important to talk about supply regulation. Okay? Because if you actually look in a lot of these critical blocks, you'll actually see they're sort of chock full of regulators, just to try and make sure that you don't get screwed up by these big supply noise on the rest of the chip. So just as an example that we talked a lot about already, in a lot of the PLLs, you'll actually see a supply regulator directly controlling the supply of the oscillator. Similarly, actually, even if you look in the data slicers, again, if you really want to receive these relatively small voltage signals, pretty easy for a 100 millivolt glitch on the supply to completely destroy your ability to see those things, right? So indeed, it's fairly common for you also actually to regulate the supply of things like your high-speed receivers, your DFEs, and so on and so forth. Okay? So again, the sort of take-home message here is that if you do a good, or alternatively, of course, a bad regulator design, I could very easily make or break the overall performance of your link. Okay? So worthwhile to actually sort of pay attention and think about this. Okay, so before we dive in, I thought it's just actually sort of useful to talk a little bit about, when I say a supply regulator, what is it that I really mean? Or in fact, what are the different types of regulators that I could potentially be using here? So there's really, I think, sort of two maybe key categories or distinctions to be talking about. So the first is what's called a switching regulator versus what's called a linear regulator. Okay? So a switching regulator is something where, generally speaking, you do some sort of pulse width modulation or some sort of other AC modulation on some DC voltage. You pass it through some kind of low-pass filter, which you build usually with passive elements. And then on the other side, you try and get a different DC voltage at the output. Okay? So these are things like buck converters, which typically have big LC filters in them, or switch capacitor converters, which are shuttling charge back and forth on different caps. Okay? But kind of maybe the take-home message from our standpoint, at least for the purpose of this lecture, is that at least for now, the biggest categorization between, let's say, the switching converter and the linear sort of regulator that you guys may care about is sort of whether or not it's easy to build it on the chip. Okay? So as we'll see in 1 second, linear regulators, really, really easy. It's basically just a bunch of transistors with, maybe some decoupling capacitance, but basically a bunch of transistors. Whereas switching converters, because as I mentioned, what you really have to do is sort of do some sort of low-pass filtering or really energy storage, that tends to imply that you need lots of big, hefty passive components. Okay? That's not to say that you can't do them, but, at least so far, they're not super popular yet. Okay? Now, there are some, let's say, efforts being done to try and make them become more common. But it turns out, for reasons that we'll talk about in 1 second, even if you had one of these switching converters, you'll tend to want a linear regulator either on top of it or in between that and the real supply, just to do a sort of quote-unquote cleanup function. Okay? So by the way, I should mention that in a switching converter, ideally speaking, sort of the voltage you get at the output doesn't necessarily set the efficiency that you would get, meaning it doesn't necessarily have an implication on how much power you would get to control that voltage. Whereas in a linear regulator, as we'll describe in 1 second, controlling that voltage sort of has a direct implication on the efficiency that you can get, or really how much power you have to spend to do it. Okay? So let's actually take a look at, when I say linear regulator, what is it that I mean by that? So there's really basically two types there. One is what's called a series regulator, and the other is what's called a shunt regulator. Okay? So I'm just going to draw sort of a conceptual diagram, and we'll talk more about the details of how you implement it in 1 second. Okay, so in a series regulator, what you're really basically doing is, if you have some input, let's say supply voltage, and you want to actually get some output, and that output, well, the way I've drawn it is going to have to be lower than the input, so that's going to be V out right here. But really the key is that you're going to try and keep that output sort of as fixed as you can possibly make it. Okay? So the way you're going to do that is just take some amplifier and use it to essentially control that variable resistance that you've stuck in between the input supply and the output supply. Okay? So now this thing is called a series regulator because basically the element you're using to regulate the output is in series with the input. Okay? Does that make sense to people? Or? Okay, so now hopefully this is maybe familiar to everyone, but let's even ignore how much power that amplifier takes. Let's just assume we can make that 0, which, by the way, is a bad assumption, but we'll come back and fix that later. So if I wanted to know basically how much power is this circuit dissipating relative to the minimum power I possibly could have taken, meaning the power that I would have needed just to basically run my load, what is that efficiency? What is it sort of absolutely limited by, given the way I'm doing things?
Drop across the resistor.
You're right, it's related to that, but so, what? Like, let's just, there's a very simple form. So I'll just give you an example. Let's say that V in is 1 volt. Let's say that V out is half of a volt. So how much power are you dissipating in that resistor relative to how much power you're dissipating in the load?
The R load by R load plus the variable load.
Okay, so that's right. That turns out to be correct, but let's just say that I told you what the voltages are in the first place.
You have the same current
Say that again?
in them. You have the same current in them, so the voltage in the load is divided by the total voltage.
There we go, exactly. So the best you can possibly do is basically V out over V in, right? By the way, everything you guys said would boil down to exactly that statement, but it's usually written this way because, usually you sort of know what the V out you want is, and the V in is also relatively specified as well. Because remember, that resistor there, it's not that I really care about the value of that thing, I'm just tweaking it until I get the output voltage that I actually want. Or perhaps more appropriately, until I make sure that I maintain the output voltage where I want it to be. Okay? Now, there's another sort of alternative so-called linear regulator, which basically looks like the following. So this time, instead of shoving something in series, what I'm actually going to do is put it in parallel, or put it in shunt with the thing that I'm trying to control. So in this case, again, at least conceptually, now what I'm actually doing is basically, using this feedback amplifier to essentially try and make sure that the current that's flowing from the input is basically fixed, right? Because if the current is fixed, then now also the voltage should not be changing. Okay? Okay, so now if I just sort of, so this time around, obviously everything is sort of set by current. So now, what would be sort of the best possible efficiency you can get from something like this? I've just labeled sort of, the total current versus just the actual current flowing into the load. Now what's the efficiency?
So ratio of
Say that again?
Those are only two variables. It's a ratio of the two.
Okay, there's only two variables. That is the correct answer. So it's just the ratio of the two, right? So it's just the load current divided by the total current. Okay, for kind of the same reasons as we just said happened with the voltage. Okay? Okay, so now I've kind of given a hint about this already in sort of the text that I put here. But it turns out one of these is really good for isolating circuits from other circuits that are noisy. And the other one, its real main purpose is to essentially keep the impedance of the supply as low as you can possibly make it. Now, first of all, which one is which? Which one is sort of good at isolating things? And which one is actually good at, or really its main purpose is just lowering the impedance? Somebody who hasn't, who's not in my group or hasn't heard my thesis or whatever.
That's bad, right? If someone hasn't read a thesis, by the way.
No, well. This is true.
No one answered that question.
What's that?
So no one answered that question.
No. So let me give you guys an example. Let's say that you've got, well, and actually let me maybe ask you guys. So if you've got a 100-watt microprocessor, how much power, out of that 100-watt budget do you think is spent on all of the links in the entire system? Roughly speaking. How much power do you think they budget to the IOs?
5%.
Yeah, 5 to 10%. So in other words, maybe 5 to 10 watts for the IOs. Okay? So that means you've got something like 90 to 95 watts from the processor itself. Okay? So, let's just sort of pick, one approach and see what happens. So let's say that you really want to make sure that these links see a very, very clean power supply. Okay? Let's say that you tried to do that with a shunt regulator. How much current, roughly speaking, would this thing here have to be dealing with to get you a perfectly flat flat voltage? How big are those current changes?
0 to 95 amps.
Yeah, something like 0 to 90 or 95 amps, right? Because if the processor can do whatever the hell it wants, and in fact maybe this is even the average, so the transients could be even worse than that, this thing has to be dealing with something like 90, up to 90 or 95 amps, right? And in fact, by the way, because of the particular way I drew it, obviously this thing can only pull current out of the power supply, so that generally means that you have to pull more current than you really wanted and then back off, right? Okay, so what did I basically just do to the efficiency of my whole processor?
Killed it dead.
Yeah, I basically made it half, I doubled the amount of power I was spending, roughly speaking, right? Okay, well, if instead I actually used the series regulator, and I just put this series resistance in between the main global supply and my actual high-speed links, even if I was really crappy with this, let's say I only had 50% efficiency with that, which, by the way, we'll do better than that in 1 second. How much extra power am I going to spend? So now I'm only putting the series regulator on top of my links. How much extra power do I spend?
V-Link over VDD.
Say that again?
V-Link over,
Yeah, V-Link over. So let's say I was only 50% efficient, which is really crappy. Then I would only burn an extra 5 to 10 watts, right? And by the way, if I did that, then now notice I can keep this really, really steady, even if this global supply is moving around all over the place, right? We'll talk a lot more about exactly how we do that, but that's really kind of the key distinction to keep in mind, is that if you have a circuit that's relatively low power, and it's not really the source of most of the variation, it's always better for you to isolate it from the source of the variations than it is to go after those variations in the first place, okay? Because the point is, if the variations are associated with really, really big current changes, it's really painful to try and fix them, right? You'd much rather just bite the efficiency on the thing that's, maybe not, that maybe is not the most power, but instead you can make it really, really clean and not actually pay all that much real penalty for it, okay? Does this make sense to people, or? Okay, great. So, if that makes sense, that's why for most of the rest of the talk I'm really going to be focusing on sort of the,
So, what you've said is the series link is good for isolating you from power supply because it does so in a power efficient way.
Well, I wouldn't necessarily say it's a power efficient way. It's just that if the other thing that's causing the variations is way, way bigger power than you, I'd much rather bite it on this than deal with the big variations.
Sure. I guess it's not immediately clear to me why the shunt link is better for controlling your impedance.
Okay. So that's fair. Now, this shunt link here, it all depends on, let's say, what's the objective function you care about, right?
Mhm.
So remember, I mentioned here that sort of, in order to get into the picture in the first place, at least if I do it this way, then what I basically have to do is sort of burn extra current, right? So what is true is that both of these feedback loops can actually create sort of a virtual low impedance at this node, or equivalently at this node here, right?
Mhm.
The only trick is that with this loop here, right, the way I create low impedance is I just make sure that I just sort of grab all of the current variations from here and I shove them out onto the global supply, right? But I really didn't do anything to fix the impedance of that global supply.
Mhm.
Right, so that kind of means that that global supply is still going to have as big of a variation as it used to. In other words, what I'm just going to have to do is make sure that I've sort of always kept this low compared to all of the big variations I see on the global supply. Whereas here, because I'm directly sort of futzing with the current, now I can really just make it so the impedance I see looking back there is small, right, without necessarily dropping the value of the supply.
Mhm.
Does that make sense? Or?
Okay.
It's a good question. Yeah.
So in the case of the microprocessor, do you prefer the shunt or series?
Okay. So for the processor itself, it turns out you can't exactly do... So the series is definitely bad. That's completely out. You can't exactly do this one because of the reasons that I just mentioned, which is, if I'm going from, let's say, transiently anywhere from 0 to 200 amps with a 100 amp average, that means I basically need to be burning an extra 100 amps so that when the processor demands more, I can back off, which clearly is not what you want to do. So instead, what you really do is you build something that allows you actually both to draw current out and to push it in. Okay, so that means you need an extra supply voltage and things like that. But once you've done that, you do indeed prefer a shunt. Good question. Other questions on this? Or? Okay, great. So let's actually start taking a look at how we're going to do these series regulators, and in particular, what some of the requirements on these things might be. Okay? So the first one, which is usually particularly relevant in sort of the high-speed link case, is that you want what's called a low dropout voltage. So dropout voltage just really means, you've got this sort of variable resistance thing, right? But you can kind of imagine there's sort of a minimum resistance that you can implement, right? So in other words, if there's some minimum resistance here, that kind of implies that there's some minimum voltage drop between the input and the output, okay? Now in particular, you usually don't really build this as a variable resistor. You actually build it as some sort of, CMOS transistor that you usually want to keep in SAT. Because if you keep it in SAT, then you have sort of reasonably good control over the output voltage. So that dropout, or that basically minimum voltage drop, is usually associated with sort of keeping a transistor in saturation. Okay? So the first thing that you do indeed typically care about is basically making that dropout as low as you can make it. In other words, making the difference between the input supply and the maximum output supply as small as you can make it. Okay? There's actually there's a couple reasons for that. So one is that, as we said before, our efficiency is sort of limited by that ratio of voltages. So the closer we can make the output to the input, the better the efficiency we can get, right? The second is that don't forget, you actually have to budget for the fact that transiently that input supply could actually be dropping, due to just dynamic currents that you're dumping into it. So if you really want to keep that transistor into SAT, you have to actually margin for all of those variations on the input supply too. Okay? The other sort of really critical requirement, which in the case of links is why we sort of got into this business in the first place, is what you really want is make sure you have high power supply rejection ratio actually really across a broad range of frequencies. And by power supply rejection ratio, I just mean essentially sort of the ratio, if I have a certain amount of variations on VDD, how much variation I got on the regulated supply, and I just take the ratio of those two. Right? So the bigger the rejection, the better. Okay? And by the way, you really do need this typically across a big range of frequencies, because a lot of times, especially for example if you're using something like a ring oscillator in your PLL, the kind of intrinsic rejection you get from your load circuitry may not be that high. Okay? So a lot of times you're actually using this regulator explicitly to try and clean up any of the issues that your load circuitry may have had if you see any significant supply variations. Okay? Make sense to people? Or? Okay, great. Okay, so let's actually take a look at how you'll typically build something like this. And it turns out this is one of those circuits where the actual transistor count that you need to do this is probably, here, I guess if I just map this diagram, this would be like 6 transistors. But actually, as you'll see in 1 second, or actually as we go through the lecture today, we can spend a lot of time talking about just these 6 transistors and how hard or annoying it is to actually build this. Okay? So let's just sort of, look at this a little bit more carefully. So all I've done here is, I have some amplifier, I have some PMOS transistor that is basically acting as my variable resistance. And so obviously this feedback loop here, all it's trying to do is just make sure that this voltage right here is just tracking my reference voltage. Okay? Okay, and by the way, it is indeed the case that you will typically build that amplifier out of something really as simple as this just sort of, current mirror loaded differential pair. Okay? Okay, so now there's a couple of important things to notice here. So the first is that, remember, I said that I wanted a low dropout voltage, right? And by the way, a lot of times low dropout regulators are called LDOs. So just, I don't know why they skipped the V or whatever, but somehow that stands for low dropout voltage. Okay? Okay, so if I want a low dropout voltage, what does that sort of imply about this transistor right here? How are you going to want to sort of design that thing?
Star.
I heard somebody say it.
Low V star.
Yeah, you want a small V star, right? Because basically the smaller the V star, kind of the smaller the voltage drop you need across it to keep the thing in sat. Okay, so what else does small V star imply?
Size. Larger size, low.
Yeah, right? It's going to be a big device, right? Well, guess what? If it's a big device, that means the gate cap is going to be big, right? Well, hey, if I've got a big gate cap being driven by just, some current mirror loaded differential pair, that means I'm going to have a relatively low frequency pole at that gate node, right? So I've got one low frequency pole. Okay, anywhere else where I'm probably going to end up with a pretty low frequency pole in this circuit?
Output node.
I heard somebody say it.
Output node.
Yeah, the output node. Why?
Decap's big.
Yeah, exactly. You want a big decap, right? And the reason you want a big decap is obviously, at higher frequencies, the bigger you make that decap, the better, the more stable your supply will be, right? So indeed, notice I now have 2 relatively low frequency poles, right? Okay, so if I have 2 poles that are close to each other, what do I have to do?
Zero.
Say that again?
Zero or compensate, split.
Yeah, I need to compensate this thing somehow, right? Because if I just sort of nominally take this thing, maybe I just got really, lucky, but generally speaking, those things line up pretty close to each other, and you're screwed, okay? So basically, you have to compensate this thing, okay? Well, okay, so what's like the first thing you might do if you tried to compensate this thing? What's like the classic compensation that, everybody beats into you the first class you ever take?
Pole splitting.
Say that again?
Pole splitting.
Pole splitting, yeah, so otherwise known as Miller compensation, right? So usually you just take a cap, you throw it from the gate to the drain of that PMOS transistor right there, right? And indeed, this is a beautiful compensation technique from the standpoint of compensation. Sometimes you might also do something like this RC filter, right, which is kind of a similar idea, like you're inserting a 0 into that thing, but you're also, moving one of the poles down to lower frequency. It has sort of similar effect, although, as we'll discuss in a little bit later on, this maybe is actually a little bit better than the Miller in this particular case. But actually, for both of them, what is it that you're doing to achieve that stability? Like, how is it, what's the main effect that's being used to actually make that thing stable? Or to say it another way, which one of the poles is usually the one that you're sort of mucking around with?
The gate.
Yeah, the one at the gate, right? That one, by the way, is associated with the amplifier. What is it that we're usually doing to the amplifier to make the thing stable?
Reducing its bandwidth.
Yeah, we're making the amplifier slower, right? What we're really usually doing is slowing down the amplifier to achieve that stability. Okay, so if we're slowing down that amplifier, the question then becomes, well, okay, hang on, we had that amplifier there in the first place because we wanted this whole thing to give us good supply rejection. right? So the question really becomes, if you just do this typical compensation thing, which by the way will make the loop work, what's that going to imply about how good of a supply rejection you're going to get? Okay? So let's actually sort of take a look at that. Okay, so this picture that I'm showing here is a little bit of, let's say, a cartoon in the sense that it's not really apples to apples, so to speak, but it's at least just to give you the idea of why what we just said may not actually be a very good idea. Okay? So what I'm going to do now is I'm going to just sort of do a very simple comparison. So in one case, which is going to be the case in blue here, basically what I'm going to do is I'm going to say that in this system I have two poles. Okay? So in the blue case, I'm going to make it so that the pole that's at low frequency is sitting at the output, and the pole that it's a high frequency is the amplifier. Okay? And in the red case, I'm exactly going to flip it. Right? So I'm going to put the low frequency pole in the amplifier, and the high frequency pole at the output. Okay? Well, so anyone notice a quote-unquote minor difference between these two? Which one of these would you choose to have in terms of your supply regulator? And by the way, this axis here, that's supply sensitivity, meaning that, if this is only, let's say, minus 2 dB or whatever, that means that there's only 2 dB difference between the supply variations and the output voltage variations. So which one of these two which one is good? Or which one is at least better than the other?
Output dominant.
Yeah, you want the output to be dominant, right? So what is it that we do when we compensate the thing? Which one are we making dominant?
Amplifier.
We're making the amplifier dominant, right? Now, by the way, why is it that this curve looks like this? Why is it that all of a sudden we get more coupling into the output when we make that amplifier dominant?
Reducing a feed through zero, something like that.
You can think of it that way, yeah. Or really intuitively the way I like to think of it is, basically this point right here is indicating to you when does the amplifier lose gain, right? So if the amplifier gain is going down, that means it's less effective in creating a negative feedback loop to control the output, right? In other words, we have less gain to correct whatever error was created at the output, right? And as I go to higher and higher frequency, I have less and less gain. Okay? Now it turns out the really bad news is that if you actually do this right and you actually stabilize everything, kind of by definition, you have to throw away all of the amplifier's gain by the time the actual output decap would kick in order to make this thing stable. Okay? So that's why you can see there's this huge difference between this red curve, which is where I made the amplifier the dominant pole, versus the blue curve, which is where I made the output the dominant pole. Okay? Okay, so what this is kind of telling you is that, even though we obviously need to make these things stable, what we'd really like to have happen is to get as high of a gain bandwidth as we can in that amplifier. Right, because the higher we can make that gain bandwidth, the more likely it is we can actually get this thing to be stable and give us good performance at the same time. Okay? And remember, traditional compensation does exactly the opposite. So that's going to tell you that, okay, well, can't quite do that. You have to come up with something else. Okay? Okay, so to sort of figure out what is that something else that you're going to do, what I want to do now is sort of turn the question around a little bit, right? Because what I basically just said is that, I really want my gain bandwidth to be sort of as high as I can get it. But why is it that you can't make that gain bandwidth sort of, infinitely big? What do you have to pay for it? You have to pay power, right? Because the more gain bandwidth you need, the more power it's going to cost you, right? So what I want to do is flip the whole question around now. So instead of saying, let's just make gain bandwidth as big as you can, let's actually ask, how much gain bandwidth do you need for a given PSRR? Okay? And in particular, what I want to see is, as I change that PSRR, what's going to happen to my gain bandwidth requirement? Okay? So it turns out that in order to do that, we have to sort of take, a couple of, let's say, intermediate steps. Right? Because I hopefully have sort of convinced you as to why you want to make the output dominant and not the amplifier. But really, I haven't necessarily done the best possible thing I can do. Okay? And what I mean by that is that, in general, if I have some amplifier, even if I fix the gain bandwidth, I still have sort of the freedom to choose between how much gain I use and how much bandwidth I get, right? And I can always sort of trade between those two things. So in order to answer this question of how much gain bandwidth you really need, I first have to answer the question of, if I told you how much gain bandwidth you had, how should you really design that amplifier? In other words, how much gain should you use, and how much bandwidth should you use? Okay? So it turns out there's lots of different ways you could potentially do that. But in order to really do it, I first have to be a little bit more careful as to what it is that I mean when I quote power supply rejection ratio. Because you can imagine power supply rejection ratio actually, there's many different values for that, right? Because every single frequency has actually a different value of power supply rejection ratio. So for the results that I'm going to walk through today, I'm just going to define power supply rejection ratio as always being basically the inverse of whatever the maximum sensitivity was across all frequencies. Okay? So if I had a curve, for example, that looked like this, I would quote that peak right there. Okay? That's maybe a little bit bogus, but as you'll see a little bit later on, you'll never end up with curves that look like that if you really do this optimization correctly. Okay? Another thing that you could optimize would be, for example, to say, well, let's assume that you have white noise on the power supply. And then let's minimize the integrated supply voltage noise at the output. Okay? Turns out if you do that same thing, then actually you'll get very similar results. If you do this, you'll get very similar results to what you get by doing this. Okay? And the intuitive reason for that we'll see in 1 second is that it turns out once you do this optimization, basically the curves that you get in terms of what the optimal, let's say, supply sensitivity looks like are relatively flat. Okay? But again, we'll talk about that in more detail as we go through. Okay? So everybody good with at least, the setup of what we're trying to do? Okay, so obviously in order to do that, even though I sort of showed you a couple plots already, I obviously glossed over one important thing, which is, well, hey, what sets the power supply rejection ratio in the first place? Okay? So typically speaking, you'll find that by doing some sort of a small signal model for the regulator. Okay? So, reminder, this is really how the regulator is built. But if we sort of look at the small signal model for that, then it's fairly kind of easy to understand where it's coming from. So if I'm interested in supply rejection, then I just set the reference at least to be, let's say, AC ground, right? I replace this thing with what's really inside of it, which is obviously just some transconductance cell driving some load resistance with some gate capacitance, right? The PMOS transistor I just replaced with its small signal model. So that's a GM controlled by that control voltage right there. That's an RO tied to the supply voltage. And then, of course, I have my decoupling capacitance down to ground over here. The only other thing that's important to mention, which sometimes people forget about, is that this load right here, the actual circuit you're driving, usually has some incremental resistance associated with it, right? In other words, if you make a small change in the supply voltage, you'll get some small or perhaps large change in the load current. Okay? So when you do these kinds of sort of small signal models, you really have to include that linearized or small signal R load. Okay, now you have to be a little bit careful with that because that small signal thing is not the same as the large signal. Is that what your question is? Yeah.
How about the gate cap of the PMOS?
Okay. So in reality, that gate cap should actually be tied up to VDD over here. Okay, but I've played a little bit of a clever game, which keep in mind because I'm going to come back to it a little bit later. Notice this GM here, I've referenced to that delta VBP. And that delta VBP, I've referenced to AC ground. Okay? Now, in reality, if you really look at this circuit right here, what you really want is this VBP. That node is really referenced to the supply, right? So I've actually made one, let's say, clever but actually very important assumption here, which we'll come back to later, which is that I've built this whole thing in a way that basically this node is indeed perfectly referenced to the supply. Meaning if the supply jumps, VBP also tracks with it perfectly. Okay? So that is indeed a simplification I've made in this model. And we'll come back to that one later because if you don't get that right, big trouble ensues. Okay? It's a great question. Other questions on this? Or? Okay, so before I give you the actual transfer function, let me just define a few parameters that are sort of useful for us to work with instead of doing GMs and ROs and things like that. Okay? So first of all, what I want to do is define this AO, or A0, as just being the gain of the PMOS power device. Okay, the voltage gain of that PMOS power device. So using this small signal model, what is that voltage gain? So just from delta VBP to Vreg, and both of them again referenced to ground, what is that voltage gain? By the way, nothing magic here. By the way, what kind of amplifier is this thing? If you look at it like this, what kind of amplifier is that? And by the way, I just want the gain at DC.
Common source amplifier.
Yeah, it's a common source amplifier, right? So what is the gain of this thing? Yeah, it's just GM times RO in parallel with R load, right? Again, nothing magic. Simple common source amplifier. Okay. What's the pole associated with that output node? What's that set by? And again, the output node is this point right here.
It'll be the effective GMA, ROA by.
Oh no! So I just want the pole. I'm not. So sorry. Let me be careful. I want the open loop pole. Okay. So I haven't tied any really feedback or anything. I'm just asking for open loop parameters right now. Yeah, it's just 1 over RC, right? So in other words, it's 1 over RO parallel with R load times CD cap. Okay? Okay. Now let's define the voltage gain of the amplifier. And again, this is going to be the open loop voltage gain. So what's the open loop voltage gain of the amplifier? Again, nothing magic here,
ROA.
Yeah, there we go. It's just GMA times ROA. Okay? Okay, similarly, what's the open loop pole of the amplifier? Again, open loop.
Or ROA CGP.
Yeah, there we go. It's just 1 over ROA times CGP. Okay? So I'm defining all these parameters because it turns out that with this particular system, it's actually much easier to think about it with these voltage gains and open loop poles. And there's actually really just one more thing that's kind of useful to define. So it turns out with this particular thing, even if I threw away the amplifier and I just didn't have the amplifier there, but I just had this PMOS transistor, it was just magically biased at the right spot, you'd basically get some attenuation between variation on the supply voltage and variations on this output, and both of them again being referenced to ground. What is that attenuation created by? And again, just assume this delta VBP, it's kind of not doing anything for you. It's just fixed. Say that again?
Gap ratio?
I don't see any. Well, okay. In reality, there is, but I don't see any cap from here to there. At least not open loop. Not in my model that I drew. Yeah, it's just the resistive divider ratio, right? So even if I don't have the feedback loop, I don't really do anything. I will at least get that resistive divide ratio, right? So I'm just going to define that as what I call SVDD. That's kind of like the sensitivity to the supply voltage. But again, it's completely like open loop, right? And that's just going to be R load over R load plus the RO of the power transistor. Okay? And again, I'm just defining things this way because it's going to keep all my expressions at the end of the day much cleaner. Okay? Does this make sense to everybody? And by the way, I haven't really done anything yet. I've just defined a bunch of terms.
Isn't it 1 over GM instead of RO? Because
no, because so again, this is something that's slightly subtle. I'm again assuming that this transistor here, that when I move the supply, the gate to source of that transistor is not changing. Okay? And that's kind of why I drew, it's a little bit funny, but that's why I drew things this way. So this GM is really controlled only by that delta VBP. So in some sense, you can think of this as, that being broken there, and this just being a ground connection like this. Okay? Okay, so if everybody has that, then now actually, you can do a little bit of algebra. We don't necessarily have to do it. I'll actually give you the final result. can very easily come to the following sort of expression. So if you want to know what's basically the transfer function from VDD to the regulated output voltage, what you get is the following expression. You have S VDD times 1 plus S over omega A divided by 1 plus S over omega A times 1 plus S over omega out plus the gain of the amplifier times the gain of the output stage. Okay? Okay, so now this at least intuitively makes quite a bit of sense, because as we said before, right, when that amplifier starts losing gain, right, that's when you start seeing more coupling into the output, right? So in other words, that means indeed there should be a 0 at whatever the open loop bandwidth of the amplifier was, right? And then this thing down here on the bottom, that's just sort of your standard second order system, right? So obviously the more loop gain you have, at least at DC, the more you'll attenuate things relative to that nominal resistive divider you got in the first place. Okay? Does this make sense to people? Or again, I'm not expecting you to derive this in your head, in the last 30 seconds or whatever. Just, take this as being correct for now, and then feel free to go back and rederive it later. Okay, so if you sort of, believe me that that is indeed the transfer function, well, turns out we can take that transfer function, and as we were saying before, I can basically figure out, parametrically speaking, as I sort of change the characteristics of the amplifier, what is indeed going to be the worst case sensitivity you get. Then, take some derivatives, set them to equal to 0, solve a whole bunch of math, and then figure out what is really the best way to design that amplifier to get the lowest worst case sensitivity for a given gain bandwidth product. Okay? So just to make that result a little bit more clear, and again, sort of, to get rid of some extra stuff that doesn't really matter, what I'm always going to do is kind of normalize the performance of that amplifier in comparison to what was the output pole dynamics in the first place. Okay? So in other words, as an example, for the bandwidth of that amplifier, I'm just by definition going to say that that amplifier bandwidth is some factor kappa times the output pole bandwidth, or the output pole. Okay? And again, I'm going to do things this way because it's going to turn out it'll give us some very direct intuition into how we want to actually build this thing up. Okay? So once I've done that, the other thing I can then do is just define a normalized gain bandwidth in that amplifier, where that normalized gain bandwidth, which I'll just call GBW, is just equal to kappa, which again is dimensionless, times the gain, the voltage gain of the amplifier, which of course is also dimensionless. Okay? So, turns out again, if you walk through a whole bunch of math, and again, if you're interested, you can go sort of check out my PhD thesis. I talk about how you get there in the first place. Once you walk through that math, what you'll find is that as long as your open loop gain is reasonably large compared to 1, the following optimal design gives you the best worst case power supply rejection ratio. Okay? So that optimal design does the following. So this kappa, remember that tells you how big of an amplifier bandwidth you want relative to the output pole. Okay? So what this equation is telling you is that the optimal bandwidth for you to use in the amplifier is set by square root of 3/2 times the output stage gain times that normalized gain bandwidth you have. Okay? Similarly, if you look at how much gain you should be using, that's equal to square root of 2/3 times the gain bandwidth, but this time divided by that output stage gain. Okay? So there's a couple of things you should sort of notice here. So first of all, if I increase that output stage gain, that tells you you should increase the bandwidth of your amplifier. But at the same time, if you increase that output stage gain, you should actually decrease the voltage gain of the amplifier. Okay? So we'll draw a picture that sort of, gives us a little bit of intuition to why that is happening. But just keep that in mind. Okay? The other thing, which again should sort of hopefully be obvious, is remember I said that, we're always going to want to figure out how things move when you change the gain bandwidth. Well, this is telling you that, hey, okay, if you increase the gain bandwidth, basically you should be increasing both the bandwidth of the amplifier and the gain of the amplifier in kind of the same way, right? They're both scaling with a square root of that gain bandwidth. Okay? So because I know this is kind of heavy on the math, what I always like to do is to kind of draw a picture that now tells you kind of intuitively why it is that you might end up with a result like this. Okay? So let's just sort of redraw our small signal model. But this time I'm going to draw it a slightly different way to, I think, make it more apparent what's really happening here. Okay? So first, of course, we've got that, that supply voltage, which we're putting small signal variations onto, right? We've got the output resistance from our PMOS power transistor. We've got the load, the linearized load resistance. We've, of course, also got that decoupling capacitance. Okay? Now, before I draw anything else, let's say I was interested in just if I just had this network by itself. So somehow I magically broke the feedback loop. Right? So now really all I have is I have the output resistance of that PMOS transistor, and I've got sort of this, RC network down at the bottom. If I was interested in this sort of transfer from VDD to VREG in this open loop case, what would that look like versus frequency? What's the shape of that?
So it's like a low pass.
Yeah, it's just a low-pass filter, right? This is just a first-order RC network. It's just going to look something like this, right? I'm just going to label, what colors represent which curves now, okay? So by the way, where does that curve start from? What is this value right here? Using the terms that we defined. Yeah, it's exactly SVDD. Okay? Okay, well, so this is telling you if you did absolutely nothing, this is the supply sensitivity curve you would get. Okay? Now let's look at what the amplifier is really doing. So if I have that amplifier, what I'm basically doing is I'm grabbing that voltage there. I'm amplifying it, but, with only some finite bandwidth. And then I'm using that amplified value to actually control a GM. Right? And the GM I'm using is actually the GM of the output stage. Okay? Well, if you kind of remember, hopefully from 240, we sort of did this transformation many, many times. Right? If I look into that direction, I'm kind of seeing an equivalent impedance. Right? So by the way, what is that equivalent impedance that I'm seeing? And just as a reminder, that amplifier is just a first-order low-pass system with, a gain of AA and a bandwidth of omega A. So what is the impedance you see there?
1 over GM over 1 plus A.
Say that again?
1 over GM over 1 plus A.
It's actually not 1 plus A, because notice the only way I get back to this gate here is through that A. Right? So what is it?
1 over AGM.
Yeah, it's just 1 over GM times A, right? So in other words, and I'll just write that out, it's 1 over GM times AA of S, which, by the way, is just equal to 1 plus S over omega A, divided by GM times AA. Okay? So at DC, you get A times larger than the GM, at least in terms of conductance, right? Okay, so now here's the question. Physically, how is it that creating that lower impedance is allowing you to get better power supply rejection ratio? Like, what is that? How is this thing, what is this sort of showing up in comparison to?
Start from a lower point.
Yeah, you start from a lower point, but let's say, given this, impedance-based model that I'm looking at, what is it, why is it that it's good to have a lower impedance created by that amplifier there?
Lowers your decap or your output pole because that impedance is smaller than your load.
Okay, it is smaller than the load. I'm not sure it's the decap itself, but it is smaller than the load.
So it makes the lower branch lower impedance compared with the RO.
There we go, exactly, right? What you're basically doing is you're taking this low impedance and you're putting it in parallel with that R load, right? So in other words, you're lowering the impedance of that entire lower branch, okay? So it turns out that the relevant quantity you're actually going to want to look at is basically that amplifier impedance relative to essentially the net impedance that's at that point. Okay, and I've done this way because, conceptually, I guess it's easier to think about it as just being relative to our load. But if I do things this way, then it's actually easier to sort of see what's going on. Okay? But really, conceptually, all we're really doing is, we're dropping that impedance, which makes us have a more favorable voltage divider, right? So if I look at that particular quantity, which, by the way, just turns out to be 1 plus S over omega A divided by the open loop voltage gain, right, which is why I picked this particular normalization. So if I look at that thing, and now I just want a plot of what does that do versus frequency. Okay? And let's do that this time in blue. So what does that sort of, normalized amplifier impedance do versus frequency? What does that plot look like? Yeah, exactly. It's a high-pass filter, right? It's a high-pass behavior, right? So you start somewhere, and then you start kicking up, right? And of course, this is a more straight line than I drew it. Something like this, okay? Now, by the way, I should label some of the frequency points here. So back when I had this RC filter here, the pole there is just omega naught, right? It's just the output pole. I didn't do anything to that thing, right? Okay, but now, if I plot this thing here, where is it that basically, let's say in terms of the parameters I gave you, where is it that that thing starts losing rejection, or rather that let's say the coupling starts getting larger? Like what frequency is that at?
Omega A.
Yeah, it's at omega A, okay? So roughly speaking, that would be omega A. Okay, now, here's where, let's say, looking a little bit at the math is actually useful. Okay, so remember this kappa here, that number is the normalized bandwidth, right? It's the normalized bandwidth of the amplifier compared to the bandwidth of the output node. So let's say that my normalized gain bandwidth is like 1, okay? Meaning that I have the same gain bandwidth as in my amplifier as I have bandwidth in the output node. What would that kappa be? Would it be greater than 1 or less than 1? In other words, is my amplifier bandwidth larger or smaller than the output node bandwidth? By the way, does your output, does the output stage usually have gain greater than 1 or less than 1?
Greater than 1.
Yeah, greater than 1, right? So basically, if I say that this normalized gain bandwidth is 1, right, and I say that this thing is greater than 1, then my normalized bandwidth is also greater than 1, right? But now here's where things actually get interesting. What happens is I actually increase that. If I make the output have more gain, what does that tell me I should do to my bandwidth?
Increase it.
Yeah, you also want to increase it, right? Well, okay, so intuitively what's really happening is that when I drew this picture here, I didn't sort of draw it just by accident, okay? I actually intentionally showed that the point at which that amplifier starts losing gain is actually pretty much lined up with the point at which this RC filter curve basically crosses with the rejection you were going to get in the first place, okay? So in other words, if I really looked at the sort of overall response for this thing, what the equations are really trying to tell you is that basically, if I looked at the overall response, what you're actually going to get is something that looks sort of like this, okay? And really the only difference between the blue and the black there is that the black, if I do things exactly correct, down at DC, should just be that, okay? Whereas the blue does not have that 1 plus factor, okay? It's just SVDD over AA, A0. So let me just write that in. Okay? So kind of just to say this another way, what we're really doing is we're taking the impedance that's created by this amplifier and putting it in parallel with the impedance that's just coming from this RC filter. Okay? So if you really sort of look at it a little bit more closely, what those equations are trying to tell you, what that optimization is trying to tell you to do, is to make it so that the impedance you get from the amplifier is basically maintained at whatever you want it to be. In other words, it's flat, all the way up until the point it meets the impedance of the RC filter. Okay? Does that make sense to people, or? Okay, so now here's kind of the crux of this whole question, or this whole story. So if you follow that rule, which again tells you that you always want to make the amplifier maintain the same impedance all the way up until the point where the RC filter gives you that impedance, and then you can let go of the amplifier. What happens when you want to get better rejection? And in particular, let's say you wanted to improve your supply rejection by a factor of 2. What is it you have to do to the amplifier?
2x higher bandwidth.
Say that again?
2x higher bandwidth.
Okay, so first of all, if you want to improve the supply rejection by a factor of 2, you're absolutely right. You're going to need 2x the bandwidth. Now, why is it you need 2x the bandwidth, by the way? Like on this picture, what's causing that to happen?
You've sort of knocked down the effective sensitivity by a factor of 2,
Mm-hmm.
which means you need to go out in terms of bandwidth by another factor of 2.
Right, so, and by the way, the reason you have to go out by a factor of 2 is that's completely set by the slope of that RC filter there, right? So you need that extra factor of 2, just because by the time the RC filter picks up that factor of 2, it's a factor of 2 in bandwidth, right? Okay, by the way, are you done? Will increasing the bandwidth by 2x, is that the end of the story?
Increase the
That's
overall
the
gain.
gain.
Yeah, you have to increase the gain by a factor of 2 too, right? So in fact, that's exactly what this picture here is showing you, because I figured it would get too crowded on the previous one. What this is basically telling you is, if you want to improve things by a factor of 2 in supply rejection, you have to do 2 things. You have to increase the gain of the amplifier by a factor of 2, and you have to increase the bandwidth by a factor of 2, okay, in order to stay on that meeting point right there. Okay? Now, that's actually really bad news, right? Because what that basically tells you is, if you quadruple the gain bandwidth, you only get 2x rejection. If you 16x the bandwidth, you only get 4x rejection. If you 100x the gain bandwidth, you only get 10x the rejection, right? So to kind of flip this the other way, if you sort of now bring it back to that original question we asked, you say, okay, well, for a certain rejection, how much gain bandwidth do I need? What this is basically telling you is the gain bandwidth is scaling with a rejection squared, okay? So as an example, if you started out, with only a rejection of, let's say, 6 dB, and you need 26 dB, well, guess what? That means you have to increase your gain bandwidth by a factor of 100. Okay? That's pretty painful, right? Because very, very quickly, you end up spending tons and tons of power on that amplifier, right? Just to sort of get that rejection that you wanted. Okay? Does that kind of make sense to people, or? Okay, now, that's kind of bad news, but there is some good news. And the good news is there's actually a couple of ways we can use, specifically even in high-speed links, to actually substantially do better than this. Okay? So, and the first one actually, in many ways, is a little bit obvious. But to really sort of get there, we have to sort of, look at a couple of example numbers. Okay? So what this table here is showing you is, if you follow that sort of optimization procedure that we just talked about, and you just do this on some representative example, right? So let's say, just as an example, the output pole bandwidth is 100 megahertz, and you get a gain of about 3 from that output stage. Okay? Well, let's see what happens in terms of how much gain and how much bandwidth we need from that feedback amplifier as we change the amount of power we're spending there, or as we increase the gain bandwidth we're willing to burn on that thing. Okay? So as an example, let's say I do a normalized gain bandwidth of 1. Right? Well, if I do a normalized gain bandwidth of 1 and I have this output stage gain of 3, then basically the amount of bandwidth I need is something like a factor of 2 larger than the output pole. Okay? So in other words, I need about 212 megahertz of bandwidth. But notice, I've only got a gain of about a half here. Right? So that gain bandwidth-wise, I still work out correctly. Okay? Let's give ourselves another factor of 10 in gain bandwidth. So let's actually take gain bandwidth up to like a gigahertz or something like that. Again, in that feedback amplifier. Well, okay, so now I need something like about 670 megahertz bandwidth, but I still only have a gain of about 1.5, right? In fact, even if I take this thing up to like a gain of 100, okay, well, now I really have some actual gain there. And of course, I have to have, really, really high bandwidth to do that, okay? But notice that even up to about this point or so, all of these things beforehand are kind of saying that this amplifier is kind of stupid, right? Because this amplifier is not actually giving me gain, it's actually attenuating the signal, right? But really all it's trying to do is take that error that used to be sitting out over here on kind of an, let me take this picture maybe instead. All it's really trying to do is take the error that was sitting out on the drain of the PMOS device and feed it back to the gate of the PMOS device. And yeah, okay, it's trying to do that in a fast way, but if my gain is less than 1, this is kind of ridiculous, right? Because I could have just basically, and let me draw it over here. What I basically could have done is just said, well, okay, instead of taking a PMOS device like that, having the regulated voltage and some other, control voltage here, well, hey, why don't I just put a stupid diode there, right? Just tie a wire from the gate of that to the output, right? Because that's really all I'm doing at this point, right? Okay, well, so it turns out you can't exactly do that. Because remember, I still have to control what voltage I got in the first place, right? And this has, threshold drops and all kinds of other annoying things. But it turns out there is indeed a way that, at least conceptually, you can basically make it so that there is indeed a direct wire from the thing that's controlling the VGS of your power device and the actual output. So by the way, what is that thing called? And once you see it, maybe you'll realize that what I just gave was a slightly convoluted description of a very simple circuit.
It's a buffer.
Say that again?
Buffer.
A buffer. What kind of buffer?
Just follow.
Yeah, it's a source follower, right? So if I just have my power device, and let's just draw this sort of conceptually. I just make my power device a source follower now. Right? I'm only going to put this amplifier here for the sake of, let's say, the concept for now. So I have some reference, I have some VDD, and some VREG, right? So notice, if that VREG changes, then immediately the VGS of that source follower also changes, right? So guess what? Even without me doing anything at all in that amplifier, I immediately get a change in the VGS, right? So in fact, if we draw sort of the equivalent small signal model for this, in a similar way as to what we did before, to kind of highlight what was the effect of the regulator itself versus just sort of what's the open loop stuff. So again, we have the RO, we have the R load, we have that decap there. Well, okay, so I'm still going to get the GM that's basically controlled by that feedback stage there, right? But now because it's a source follower, even if I don't do anything at all, guess what? I get a 1 over GM right there, right? And that 1 over GM, again, is just coming from the fact that, hey, it's a source follower, right? You change the source. If the gate is fixed, you've changed the VGS, okay? So in other words, what this is saying is that now, if before, if we again look at that impedance basically created by the quote-unquote amplifier, what I now get is, instead of just having 1 plus S over omega A times that GM times AA, now that thing actually shows up in parallel with 1 over GM. So again, in other words, even without me doing anything at all, right? If I could have like the stupidest amplifier in the world, which basically does almost nothing, I will still get that 1 over GM, right? That's actually really good news, right? Because it says that if you were sitting down here in, this region over here, basically says, hey, forget about the amplifier. It's useless anyways. Just use the GM of the device, and actually you'll get just as good of a performance. In fact, even better than what you would have gotten by trying to do this. Okay? Does this make sense to people, or? Okay, so before we break, since we're almost out of time, does this exactly work the way that I've sort of shown it here, or are there some, let's say, minor quote-unquote practical issues. You know, why didn't I just draw this thing in the first place if this is such a good solution?
Increases your dropout, right?
Yeah, so if you don't do anything clever, indeed it'll increase your dropout. Now, why is it that it increases your dropout? And you're absolutely right, but just, you know, just to be absolutely clear.
So there's threshold voltage drop from the output amplifier to the feedback.
Yeah, exactly. So if I just focus on that source follower there, so let's say I put VDD in at the input, and let's say I want to maintain the same dropout as I had before, which means that I want this to go to like VDD minus V star. Well, guess what? That means the gate has to be at VDD plus VTH. So sorry, that's larger than your supply voltage, right? So unless I somehow magically give you an extra supply voltage, you can't necessarily directly do this. Now, turns out the good news is there's lots of tricks you can play to actually get around this. But indeed, you know, there's actually now some practical difficulties that are associated with really making this work. And as we'll see, that'll actually expose some other issues which turn out to be important not just in the source follower case, but in the common source case as well. So, unless there's more questions on that, I think we can break for today, and we'll pick back up with this on Thursday. So I'll see you guys then.